Hi there. Hey, this is Dr. Tech talking about question number 2 of exam 2 of spring 2019. Because this one has to do with counting probability, that sort of thing, and it is relevant to our final exam because I did not ask anything about probability in the second exam. Alright, so let's go ahead and get started with this one. The first thing I want to do is to point out a few things. The first one, so let's just read the question carefully. In the dungeon room, a player is to choose 5 different potions out of the 54 unique potions from a shelf and drink them in sequence. Okay, so the term in sequence, means in a particular order. Okay, so it doesn't quite state explicitly, but it suggests that order is important. And then the other one is you have 54 unique potions, which means if you pick the potions, um, it's without replacement because once you take one potion out of the collection from the shelf, it is no longer available to be chosen later on. Okay, so it does imply without replacement just because of that. Potions can interact, so order of consumption is significant. So this is explicitly saying the order is important. How many ways can a player select and drink potions? Explain your reasoning and express the value as a formula / expression. Okay, so let's work on this. All right, so um, there's not a whole lot to talk about, but except you have to state why you choose to calculate this in a particular way. So okay, so we can say sequence and the order is significant. Okay, order is significant means ordering is important. Okay, important. There we go. And then the second thing, oh, interesting, you guys are online. I didn't expect anyone to be online during this time, so I was just kind of recording. Um, so the question, so this part means it is a sequence. So we'll say this implies permutation. Permutation. So that means now we can focus on permutation. The question, because we have 54 to choose from, and we have to choose exactly 5 of those. So that means the total number of ways to select and drink the potions is going to be 54 choose 5, but then this permutation. So now we want to say is a permutation, or the number of permutations of choosing 5 from 54. Okay, so if this is not clear enough, you can always make it super duper clear. Basically it is P54 5, which is the same thing as 54 factorial divided by 54. Let me think about this. Okay, okay, so I got it. So it's 54 minus 5, and then that whole thing factorial. So that's answers the first part. So for those of you who want to type in text, as a question, I am on the text channel of 2020-05-13. So if you want to type anything, I am in that area, and Carol is there already. Cool.
I do have a question for full credit on this. Would we need to include the sequencing and ordering importance? Or could we just say permutations choosing 5 from 54 and show the calculation?
Well, the question does ask for let me pick a different color and highlighter. So the question did ask, explain your reasoning. Okay, so it's not using the color that I want. Pink, there we go. So the question did ask, explain your reasoning. So because we got several choices here, right? Because in order to do the counting, you could have chosen 54 to the power of 5. Okay, you could have chosen the combination of choosing 5 out of 54, and also obviously the answer, which is choosing 5 out of 54, but this time it is a permutation. So you kind of have to tell me why you choose permutation and not combination nor power. So the same thing that you have to kind of go through in your mind, to rule out the other two, you just have to kind of put it on paper and explain that to me.
Okay, got it.
Yep.
Thank you.
All right, so we are moving on to the second part, which says, out of these potions, 2 are poisonous. You may assume the player has no knowledge of any of the potions. In other words, the player does not know which ones are poisonous. What are the chances that the player selects and drink both poisonous potions as a part of the 5 selected potions out of the 54 on the shelf? Okay, and once again, explain your reasoning and express the answer as an expression. So this time we are not counting, okay, because the first question is a counting issue, okay, it's a counting type of problem. And the reason why we know it's a counting problem because the question is explicitly asking how many ways can a player blah 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 blah. Okay, so that one is asking about it's a counting problem. The second one is not a counting problem because the second one is asking what are the chances. So when it is asking what are the chances, then it becomes a probability kind of question, which automatically, usually it automatically means you have to divide the cardinality of the event that we are interested in by the total number of possible outcomes. Okay, so that's the typical thing that we have to do, or the format of the answer usually is in this format. Okay, so the probability of something, okay, E is computed as the cardinality of the event E over the cardinality of omega. And omega in this case is representing the set of all the possible outcomes from the experiments. Okay, so omega is kind of known already because that's what part 1 is for, is to tell us how many ways can someone choose and drink the potions in a specific order. Okay, so we kind of know that this answer can be plugged into here. So what we need to focus on now is what is the cardinality of E. Okay, so the cardinality of E is basically saying out of the 54 potions, 2 are poisonous. So the first thing is, okay, so we want to find out how many ways can someone choose 2 of the 54 potions that are poisonous, and 3 of the ones that are non-poisonous. So now you have to look at the 54 potions. Okay, so there we have 54 potions altogether, and out of those 54, 2 are poisonous, and 52 are not poisonous. So now the first question is, how many ways can we choose 2 that are poisonous out of the 2 that are poisonous, and 52 that are non-poisonous? 3 out of the 52 that are not poisonous. Okay. So it's at first it is a counting issue, and then we'll divide it by the cardinality of omega. Then it becomes a probability. Okay, so let's figure this part out first. Okay, so at first, let's not worry about ordering because we can always introduce permutations later on. Okay, so at first we'll just go like, okay, let's not worry about ordering. We're just looking at, okay, how can we, how do we choose 2 things out of 2, and how do we choose 3 things out of 52? So that becomes just combination, right? So it's combination of 2 because there are exactly 2 potions out of the 54 that are poisonous, and I need all 2 of those in the collection of the 5 that I'm going to drink in order for a player to die from poisoning. And at the same time, we also have 52 that are non-poisonous, and out of those 52, I need 3 of those. Okay. So this will tell me, how many ways I can pick up, 2 of the poisonous potions and 3 of the non-poisonous potions when there's a total of 54, of which 2 are poisonous and 52 are non-poisonous. Okay. But this gives me a number that's a combination. In other words, it basically says, okay, if I want to graphically represent this, okay, it means that we're dealing with a set, okay? And within the set, we have 2 potions that are poisonous, and then we have 3 potions that are non-poisonous. But they can be in any particular order because, after all, we are dealing with a combination. So now we have to come up with we have to introduce sequencing into this now. Okay. Now the part of the question that makes it kind of easier to figure out this one has to do with the player has to drink both potions in sequence. Okay, one right after the other one, in order for the poison to be in order for the poison to show up. So where is that? Oh, it doesn't say that. Okay. So I stand correctly.
I think it's the third part you're
It's the
looking
third
at
part.
where,
Oh, okay.
yeah.
Okay. So in this case, then it becomes this is the combination. So once we have the combination, you can always basically say, okay, out of the 5 potions, how many ways can we um, how many ways can we drink the 5 potions? Okay, I think that's what it's asking. So let me just read the question carefully again. What are the chances that the player selects and drink both poisonous potions as a part of the 5, but not dying yet? Okay, so because I came up with the question, so I remember that there was one part of the question that talks about, oh, you have to drink both poisonous potions right next to one after the other one in order to die from poisoning. That turns out to be part 3. Thank you for the reminder. So now that we have these 5, but these 5 are different. Okay, even though the first 2 are poisonous, they are not the same. The other 3 are also not the same. Okay. So now the question is, how do I, kind of randomize all of this stuff here? And the answer to this question is to say, well, we look at, a permutation of, 5 out of 5. Okay. In other words, I give you a basket of 5 potions, and then I'm asking you, okay, go ahead and just drink these 5 potions in some random sequence. Okay, how many random sequence can you come up with? That becomes the question. So that's why we have this portion here, because out of the basket of 5 potions, of which 2 are poisonous and 3 are not poisonous, we have this many ways. Okay, basically it's 5 factorial ways to sequence the drinking of those 5 potions. So that is now so when we look at this whole thing, this number, okay, this number over here is going to be responsible for this part here. So do we have any questions about this? No questions? All right. So the really important part is, if someone is using combination in the first part of the question, which is kind of marginal, okay, that's really not correct. But if that person also just uses combination without multiplying by 5 factorial in the second part of the question, that ratio will still work out okay. Okay, that's kind of the interesting part, is the ratio will still work out. Okay, so it has to be either permutation in both cases, or it has to be combination in both cases, but it cannot be permutation in one but combination in the other one. So the way I set up the answer right now is going to work out. Okay, so do we have any questions about this part? Okay, doesn't look like anyone has a question. All right, so in that case, we'll move on to the third part. So the third part says, fortunately, the two poisonous potions must be drunk in succession, meaning they one has to be drunk right after the other one, in order to kill the player. What are the chances that the player would die from selecting and drinking the 5 potions selected from 54? Okay, so this is once again a probability, because it mentions what are the chances, right? Okay, so every time we see what are the chances, it is asking about probability, which usually is a ratio between the cardinality of the event divided by the cardinality of omega, which is the outcome set of the entire experiment. Okay, but this time, the way we count E is going to be different, because we only need to count the cases where the 2 poisonous potions are drunk in sequence. Okay, so that is actually very handy, because now we have to look at the way we come up with this number, and then we have to say, well, that's going to be a lot more. Okay, if we look at, okay, let me just use a highlighter here. If we look at this number, this is actually quite a bit more than the actual number of cases where somebody is going to die, because in order for a player to die, that person has to drink both potions in succession. Okay, so now the question is, then how do we deal with this, right? So there are several ways to look at this. One way to look at this is to okay, let me think about how to present this. Okay, so one way to look at this is to combine the 2 poisonous potions and just say, okay, these are the 2 poisonous potions, and these are the 3 non-poisonous potions. Okay, now obviously I have not assigned the digits to these things. Okay, but it's okay. Okay, I don't have to do it just yet. Okay, and then the other way is to put a non-poisonous potion first, and then 2 poisonous potions, and then 2 non-poisonous potions after that. And you can see where this is going. So we have 2 non-poisonous, the 2 poisonous, followed by the last non-poisonous, or we can have 3 non-poisonous and then the 2 poisonous. Okay, so these basically list out all the possible ways to space out the sequence of drinking the poisonous potions, and how we put the non-poisonous potions. So if you look at each one, okay, okay, assuming that the 5 potions are already chosen, okay, so that's already done. Okay, so the how to choose those 5 potions is done by this part of the expression. Okay, so this basically puts the 5 potions in the tray. Okay, the 5 potions, 2 poisonous and 3 non-poisonous is put in the tray already, and the number of ways to come up with a tray like that is performed by this number. Okay, so let me just draw a picture over here. There we go. So, but out of that tray, how the sequence of drinking, or the ordering of drinking the potions out of that tray. Okay, so Carol has a question here. Not yet. Okay, so we're going to get to that a little bit later. So, but I first want to explain how to set up the problem, how to think about it. So this number, okay, which is just the red portion here, okay, or now the dark green portion, it's explaining how many ways we can come up with a tray of 5 potions, of which 2 are poisonous and 3 are not poisonous. Then we have to think about, okay, give me a tray of five potions, of which 2 are poisonous and 3 are not poisonous. Okay, then we have these 4 ways, okay, to space out, the poisonous versus the non-poisonous. But for each one of these, okay, we have within the 2 poisonous potions, there are 2 ways to arrange it, because I can drink the first poisonous and then the second one, or I can drink the second one and then the first one. So we have the permutation of 2 for the poisonous portion, okay, and then of the 3 that are non-poisonous, we have P33. Okay, because out of these 3 non-poisonous potions, I will call these A, B, and C. Okay, I could drink these 3 in A, B, C as an order. I can drink these 3 as A, C, B as in order. I can drink these 3 in C, B, A, and so on. So that's basically just 3 factorial, and the same applies to every single one of these. Okay, so this is also P22 times P33. Now it looks kind of suspicious, right? Because but the 3 non-poisonous potions are not even contiguous. It doesn't really matter because I know the position that they should go, right? The first, the fourth, and the fifth. Okay, so there are also just 3 factorial ways to assign each non-poisonous potion to each slot that has to be non-poisonous. So it would still come up with the same number. So it's going to be the same here. P22 times P33 and P22 times P33 again here. So we are now, if we combine everything, so now it is really just 4. Okay, the 4 is basically saying it's how where we put the first 2 poisonous potions. Okay, so it's 4 times 2 factorial, which is within the sequence of drinking the 2 poisonous potions. Which one goes first? Okay, it doesn't really matter. Either way, the player is going to die. Okay, but in terms of counting, we have to uniquely identify those because omega in this case is the number of permutations. So ordering is important. So now we also have to remember to multiply 3 factorial, which accounts for the ordering of the 3 non-poisonous potion of the 5. So this number, okay, this number here is going to be our the cardinality of E, and then now we divide it by the cardinality of omega, which is still the same omega as last time. Okay, so omega is still the same omega from here, and that becomes the answer. So the answer is 4 times 2 times 6, and then the whole thing divided by the number of permutations of choosing 5 out of 54. So that is a pretty slim chance that a player would die from drinking the potions. Alright, so let me see if I have any questions. Any questions on Discord? It's not really that simple. It's just how you formulate the thinking. Alright, so the question is, do we include C52.3 and C22 in E? Oh yeah, yes, I forgot about that. Okay, so you have to include that, which is C52.3, which is going to be the big number in this entire thing, and C22, which is just 1. Yep, thank you. I forgot about that. So you have to multiply the 52 choose 3, 2 choose 2, and then 4, and then 2, and then 6. So that entire product is the numerator of the probability. Thank you. I forgot about that. So it'd be good so far in terms of looking at this question. All right. Yes, and that's exactly why I split the problem into several parts, so that people can kind of think about it in different in steps instead of looking at the last part of the question and try to jump to that one. Now they can kind of view the problem in slightly different ways and just add new elements to the whole thing one step at a time. And Krishna is typing. I'm gonna wait until Krishna is done, then we can move on to the next question. Alright, so because C22 is 1, we don't necessarily need to write it in the answer, but I would prefer to write it, simply because, okay, so let me highlight why I would like to include C22 in the whole thing. Because this 2, let me go back to the highlighter pen. There we go. Because this 2 plus this 3 should add up to 5, that accounts for the 5 potions that are on the tray, okay? And then this 2 and this 52 should add up to 54, which is the 54 the total number of potions available to us. So the C22 may not seem like it has any significance in terms of what value it contributes to the product, but in terms of concept, it is really important because it tells us how we break up the 54 potions into 2 groups, 52 non-poisonous and 2 that are poisonous, and how of the 2 groups we want exactly 2 of the 2 poisonous ones and 3 of the non-poisonous ones. So it has significance from that perspective. All right, so if we do not have any further questions about this one, we will then move on to the next probability question, which is down here, I think question number 5. Yep, okay, this is the one. All right, so question number 5. So the first thing, just like, you guys know this already, but I just have to kind of mention it again. Just call me naggy, but I still have to mention it. Read the question carefully, because a lot of times, the question, if you read it carefully, it will give you some idea of how to answer it. Okay, it will help you narrow down, what kind of technique you need to use to answer the question. So in this case, is an example. Okay, it says a certain network protocol sends 256 byte UDP packets in a noisy environment. Okay, so do you need to know what is a UDP packet? No. Okay, but you do need to know what is 256 bytes. Okay, 1 byte has 8 bits. That is important. And TAC makes a cheap error bit counter that is only capable of to tell whether there are exactly 16 bits of error within 256 bytes. Okay, so let's stop right here. Okay, let's stop right here because I want to kind of express what are we talking about here. So I have a counter, that can tell whether there's an error, but the only thing it can do is to tell you whether there are exactly 16 bits that are transmitted incorrectly within 256 bytes. So right here we have a unit difference between which ones are erroneous and which ones are not erroneous. So it's good to kind of make use of the same unit. Okay, so right now we will go ahead and write down 16 out of 256 times 8, because there are 8 bits in a byte. Okay, so that is important. So that turns out to be, I think, 2048. Okay, so it's 16 out of 2048 bits. Okay, so that's kind of important. Yeah, you can do 16 bits is 2 bytes too. However, okay, I would not do it that way, because if you compress bits into bytes, that basically is now implying that all your error bits are packed into bytes. Okay, so either you have no errors or you have 8 consecutive errors at the same time, which is not what the question, what the premise of the question is suggesting. The question is basically suggesting that we basically spill all 16 bits randomly into the entire packet, which has 2048 bits. Yep. So yeah, don't combine it based on bytes. We have to continue to count bits. All right, so the next part says, tag set up an experiment to send UDP packets to cross-check received error for exactly 16 bits of error. And I also set up a cheap counter that will stop the experiment exactly when exactly 16 UDP packets each has exactly 16 bits of errors are counted. Okay, so let's pause again. Okay, not continue to read the question anymore. And see what this means. Okay, so what this means, okay, if I want to draw this graphically, is I made an experiment. Okay, so the experiment is having a transmitter and a receiver. Okay, so the transmitter, receiver, and it's sending. You can say that it sends the packets wirelessly, but it also has a way. Okay, these two are connected in some other way to detect errors. Okay. So it has 2 counters. Okay, the first counter is counting. It will count up by 1 if I see exactly 16 bits of error out of 248 bits. Okay, and then it has a second counter which counts. Okay, how many packets has exactly that problem? Okay, so the first counter is counting number of bits. Number of error bits per packet. Okay, but it's not a very good counter. Okay, packet, P-A-C-K-E-T, there we go. But it's not a very good counter because it only signifies the next step if there are exactly 16 of those. Okay, so it only counts. Okay, only counts when there are 16 error bits. Okay, so only when a packet has exactly 16 error bits, not 15, not 17, not 0, okay, not 20, exactly 16. Then it will trigger another counter down here to count, okay, now we have another packet, that is like this. Okay, so this is basically, counting the number of packets that has exactly the problem. And then there's one more universal counter that counts, okay, how many UDP packets have I sent so far? And out of those, how many have exactly 16 bits of error? And the whole process stops when I count exactly 16 UDP packets that have exactly 16 bits of error each. Then I stop the whole experiment. So do we understand the process? Okay, I'm not seeing any questions. All right. Okay, so that's what the next paragraph says right here. Okay, it says another counter keeps track of the total number of UDP packets sent. Okay, so that one is really just a usual counter. Okay, it would just we send a UDP packet, and this counter always goes up. Okay, but the other counter will only go up if and only if there are exactly 16 bits of error in the UDP packet. Otherwise, the other counter does not go up. When the second counter goes up to 16, then we stop the whole process. Okay. So now the question says, if exactly 57,696 UDP packets are sent when the error UDP counter goes up to 16, what is the probability P that each bit is transmitted correctly? Okay, so we know there's some kind of ratio going on here, right? Okay, so we can tell that there's a ratio of there are 16 erroneous, there are 16 packets that were sent erroneously, but each one has exactly 16 bits of error. Okay, and over the total number of UDP packets, which is 57,696. So now the question is, what is this ratio supposed to equal to? Okay, that's what it's asking. Okay, all right. So at this point, we can stop. We can pause. Okay, and then we look into our toolbox and we ask, what type of a problem is this? Is it a combination problem? Is it a permutation problem? Is it a power thing? Or is it a binomial thing? Okay, because remember, all of those are related to probability stuff. Okay, but because we are dealing with a bit, right? So a bit is either a 0 or a 1. Okay, and we are also looking at the bits that are transmitted incorrectly. So a bit can either be transmitted correctly or it can be transmitted incorrectly. There are only two possible outcomes. If we look at the transmission and the reception of one single bit as a trial, that trial only has two outcomes. It is either received correctly or it is not received correctly. Does that make sense? I hope that makes sense.
Yeah, that makes sense.
Okay, so that means we are looking at a problem that is very similar to a coin flip problem, because each trial only has two outcomes, and it is not without replacement, because if one bit is okay, the next bit can be okay too. The next bit can also be okay. So we are looking at a problem that is not without replacement. So that means we can almost right away throw combinations and permutations out the window, at least not directly applicable. Okay, they're not directly applicable. So it becomes a binomial issue. Okay, so now we are only saying that, well, out of 248 bits, only 16 are erroneous. Okay, so what exactly are we talking about? We are talking about something like this. Okay, so if P is the probability of transmitting a bit or receiving a bit correctly, and Q is the probability of not receiving a bit correctly or receiving a bit erroneously, then you can tell that, hey, P plus Q is just 1, because you can either receive a bit correctly or you can receive a bit incorrectly. There's nothing else. Okay, that's fine. So if this is the probability distribution for one single bit, then what happens when we have 2048 bits? Okay, so we raise it to the power of 2048, because each bit can be received correctly or can be received incorrectly, right? The next bit, same thing, the next bit, the same thing, and the next bit, the same thing, and so on. So obviously, if you look at this whole thing from the value perspective, this is a stupid question, because P plus Q is guaranteed to be 1, right? So 1 to the power of whatever is always just 1 itself. Okay, so why do we bother with this? So we bother with this because of this. Okay, in the first trial, okay, the bit can be received correctly or it can be received incorrectly, and the probability distribution is P versus Q. But when you look at the second bit, okay, it's the same thing, but now we have a tree that has 4 branches, because from the first bit, which can be received correctly or incorrectly, the second bit can be received correctly or incorrectly. When the first bit is received incorrectly, the second bit can also be received correctly or incorrectly. So every bit that we add to the sequence, we double the number of branches, because the P and Q are basically just added like this. So this graph by itself doesn't seem very interesting. Okay, but it is interesting from the perspective of so how do we get to this point here? Okay, if we just look at 3 bits, okay, because when we have 2048 bits, this graph is really hard to keep track of manually, because we'll be looking at 2 to the power of 2048 branches. Okay, and that's a huge number. We don't that becomes really basically impossible to track by hand. But with this one we can, right? This is just p squared cubed. This one here is p and q, so we have p squared and a q, and this one over here is also p squared and a q. This one here is pq squared, and then this one over here is p squared q, and then this one over here is pq squared, and then this one over here is qqp, so it's also pq squared, and then the last one is just q cubed. Okay, so you can, I mean, even if you don't follow me exactly, but you can see the general idea, right? So out of these, I can group the ones that have the same number of p's and the same number of q's. Okay, so these two and this one. Okay, I might have miscounted some of these. Oh, nope, I did not. Okay, so these three, are all, p squared q's, and then this one, and this one, they are all pq squared. This is a p cubed, and this one is a q cubed, right? So when we look at all of these things here, we say, oh, okay, I see that the result is p cubed plus 2p squared q plus 2pq squared plus q cubed, right? Okay, that's okay. But that's a binomial thing, okay? Because this is why we talked about the binomial distribution. The coefficient should be 3. Oh yeah, you're right. Okay, I counted 3 here, and then I wrote down a 2 over here. Thank you. There we go. But the coefficient itself is a combination kind of thing. So what combination are we talking about? This one here, it depends on your perspective. If you just want to count the number of bits transmitted correctly, then this one is 3 choose 3. This one here is 3 choose 2. This one here is 3 choose 1. And then this one here is 3 choose 0. Okay? So the coefficient of each term after we expand p plus q to the power of 3, each coefficient is a combination. Okay, so that is what we're looking at here. So that means, going back to our problem over here, we are now looking at 16 divided by 57,696, and that should be representing, okay, 2048 bits. Choose 16 erroneous ones. Okay, so if we keep p as transmitted correctly and q transmitted incorrectly, then this will have p raised to the power of basically 2048 minus 16, because these are the number of bits that are transmitted correctly, and then q is raised to the power of 16, because we have 16 bits that are transmitted incorrectly. Okay, so for those of you who say, okay, but in the other one you keep counting the bits that are transmitted correctly, fine, don't do it that way. Cross out this 16 and make it 2048 minus 16. It will come up with the same number anyway. Okay, so you can always do it this way. Okay, my stylus is not lined up very nicely. There we go. Minus 16. There we go. So instead of 16, you can use 2048 minus 16, which is 2032. Okay, it would still come up with the same number. Okay, so now you go like, but we have two variables, two unknowns, and only one equation. We cannot solve for that. Fine. Okay, cross this out, make it 1 minus p. Right? So now we can solve for it. So the question, the very last step, it says include all steps, all reasoning, and quotes of applicable theorems and formulae. So there are several, so you have to kind of mention the binomial distribution. You kind of have to mention that this looks like a coin toss problem, because each trial only has 2 outcomes. Okay, and it is not without replacement. So you kind of have to mention all of those things that I verbally said, at least, just kind of, very short form, you have to present those. But in the end, when we get to this part here, okay, we have a constant on one side, and then on the other side, we have a coefficient. which is 2048, choose 2032, p to the power of 2032, and then 1 minus p to the power of 16. That is sufficient. Okay, Brent is asking how I got 1 minus p. So q is 1 minus p because p is the probability of transmitting a bit correctly. And I think that's the symbol that I'm using in the question. Let me just double check. Yes. Okay. Oh, okay. Yeah. So the probability of receiving a bit incorrectly is 1 minus the probability of receiving a bit correctly. So that's why q is 1 minus p. Yep. So if you get to this format, at the end over here, let me circle which one I'm talking about. So if you can get to this format, I would consider the problem solved, okay? Because we only got one unknown in this case. Everything else are constants. So I know this looks still pretty nasty to solve, but hey, the computer can solve this in no time. Yep. Yep, Carol is also correct. P plus Q equals to 1, but that has to do with how you receive a bit. Can either be 1, it is received correctly, or 2, it is received incorrectly. So that's why P plus Q has to equal to 1. All right, so that kind of concludes the other question that has to do with probability. So let me see if anyone has any questions. The whole thing is also being recorded. I certainly hope that is the case because that was the intention. Yep, so the whole thing is still recorded on YouTube, so in case you want to go over this again, it is on YouTube right now. So do we have any other questions about these two? One is a kind of combination slash permutation type of problem, and then the other one is a binomial distribution kind of type of problem. Carol is typing, so I'm gonna wait a little bit. Okay, any general advice of how to break up and understand these types of questions? So you gotta be very, you gotta be clear about what tools are in your toolbox, because that means then you can choose, right? So no pun intended, because we are doing a lot of choosing in the problems that we are solving too. So let's go to page new after. There we go. Okay, so we have two different types of problems. So one type of problem is counting problems. So we got counting versus probability questions. Okay, so within counting problems, it's basically asking how many ways can we blah blah blah. Okay, this typically translates to how many ways can we blah blah blah. Okay, and then the other one typically translates to, okay, may not be exactly these words, but to the same effect. Okay, typically it will be questions of what are the chances that blah blah blah. Okay, so we have two broad categories of problems. Within the counting problems, okay, so within the counting problems, typically we want to break up and we want to identify what is an experiment. Oops. Experiment. And an experiment would be a sequence of trials. Okay, it is a sequence of trials. Okay, so now the question boils down to, what does each trial look like? Okay, in the case of throwing a dice or flipping a coin, okay, each trial has the same possible outcomes as the next trial. Okay, because the problem is not without replacement, it is quote unquote with replacement. You do not take one option out from one trial, so it is no longer available to all the subsequent trials. So that usually leads to the power counting issue, the power counting technique. Okay, because if you say you throw a dice, okay, and you say I throw a 6-face dice exactly 6 times, okay, what are the total number of ways that the numbers can come up? And ordering is important. Okay, so in that case, it will be 6 to the power of 6 because the first trial has exactly 6 possible outcomes. The second trial also has 6 possible outcomes, and so on. So it becomes 6 to the power of 6 in that case. On the other hand, we also have problems like, well, we got a box of 16 items that are unique. How many ways can we pick 3 out of those 16 items? Then it becomes a problem that has the property of without replacement, because once we take an item out of the box, that item is no longer available for later trials. So each trial removes a possibility from future trials in the same experiment. Okay, so this breaks up into 2 broad categories. One is with replacement, and the other one is without replacement. Okay, so in the case of without replacement, okay, then you also have to think about, well, is ordering important? Okay, so let's just say that you feel like, okay, I want to play lotto because because of COVID-19 and all the other issues related to COVID-19. You just want to try out your luck, okay, and say maybe I can be lucky, okay. So how do you choose the 5 numbers on your lotto ticket? Okay, you may have some process to do it, but you have to remember that in that particular case, the ordering of the 5 numbers that you have chosen is not important. Okay, so you have to break it up into permutation problems where ordering is significant, or a combination problem where ordering is not important. Okay, so Carol is asking, any general advice for how to break up and understand these types of problems? Clues includes the words, okay? How many ways, what are the chances, okay? So that breaks up into the 2 broad categories. And then you have to identify what is a particular experiment. So in the case of the transmission error, each experiment is the transmission and the reception of 2048 bits. That is one experiment. Then you look at each trial. Okay, what does each trial look like? Each trial becomes the transmission and the reception of 1 bit. Okay, then for each trial, then you have to look at the outcomes of each trial, and you ask, okay, what are the conclusions after one single trial? Okay, after one transmission and the reception of that bit, what are the quote-unquote results? Oh, I got this bit correctly, or I got this bit incorrectly. So those are the 2 possible outcomes. So when you analyze the trials and in the context of the experiment, typically you can get to one of these 2, okay, whether it is with replacement or without replacement. In the case you land on this side of with replacement, then usually it becomes just a power thing. Okay, it would be the number of outcomes per trial to the power of the number of trials. Okay, that becomes the total number of possible outcomes from the experiment itself, and it's typically in this case, it is typically a problem where ordering is important. Okay, now you have to be very careful, because when we say I'm just counting the number of bits in a packet that are received incorrectly, then ordering is not important anymore. Okay, and that's also partly why, when we go back to this question here, that's also partly why we got these combination here, because where the error bits are located, which one goes first, which one goes second, that is not important. I just need to know the number of bits that are transmitted incorrectly. So so that's one thing you also have to identify is is ordering is important, Because if ordering is important, then you're looking at permutations. If ordering is not important, then you're looking at combinations. All right. So what if the question is asking about probability? Well, if the question is asking about probability, then you have to kind of think of it as some kind of cardinality of event over some kind of omega. So this point of view applies to counting, okay? Particularly, it applies to these two kind of problems. Typically has an outcome that looks like this. But when we are asked about probability, it is also possible that we have a binomial distribution. So we have a binomial distribution, which is kind of its own thing. Okay, it's kind of its own thing because with binomial distribution, the special thing about binomial distribution is we assign probability per trial of how likely we can get one outcome and how likely do we get the other outcome on a per trial basis. Okay, so when you have a problem that has that particular nature, that each trial has two possible outcomes, and we either want to determine or we know ahead of time the probability of how often we get one particular outcome versus how often we get the other outcome, then you're probably most likely looking at a binomial distribution kind of problem, because it kind of stands out from all the other problems, because you either because you're looking at a known or you're trying to figure out the probability of the outcomes per trial. Whereas the other problems usually assume a uniform probability distribution when it says, okay, we got 5 things in this box. What are the likelihood that I get this one? Well, they're all 20%, right? Because they're all uniform. But when you're looking at a binomial distribution kind of problem, you're typically looking at a problem where the probability is not uniform. Okay, because you might be looking at a coin flipping experiment, and you say, well, I'm kind of suspecting the coin is loaded. Okay, and what would a loaded coin do on average after I toss this coin like 16 times? Okay, what are the distributions of, I get 0 head and the rest are tails, or I get 2 heads and the rest are tails, and so on and so forth. So that's kind of a clue of how you can differentiate what type of problem you're trying to solve. So I hope that answered the question, at least to a certain point. Okay, all right, cool, excellent. All right, so if there are no further questions, I'm gonna stop the stream. Oh, okay. More specifically, for the second part of the second problem in the exam, you're thinking of it in terms of the fact that there are basically 5 slots to fill potions into. 2 of them are poisonous, leaving 52. For the second portion, I think that is correct. I think that's exactly how we did it. So let's go back to the question. So for the second portion, we have that portion here, but you have to remember that we also have to multiply the whole thing by 5 factorial, because we have to look at the omega that we are, we have to look at the omega, because the omega, in the omega that we worked out in the first part of the question, ordering is important. So that means, when we come up with the number for the second part, we also want to make sure that the ordering is important. And Brander is asking, going over question 1. And okay. Let me. Okay, I'm reading the question out of the text, which turns out to be pretty small on my end, so I can repeat the question over here. Okay, so we are transmitting 110, and it is received as 110 correctly with a probability of 0.576. It receives as 101 with a probability of 0.016, and it is received as 011 with a probability of 0.016, and lastly it is received as 010 with a probability of 0.144. There we go. All right. So P is the chances of transmitting a 1 and receiving as a 0. Q is the chance of transmitting a 0 but received as a 1. Okay, so P is the probability, PR, of a 1 received as a 0, and then Q is the probability of transmitting a 0 but somehow it got received as a 1. So both are erroneous, but erroneous in different ways. So in this type of question, the probability is asymmetric. It is not symmetric. When you transmit a 0 and it got received as a 1 versus the probability of transmitting a 1 but receiving as a 0, those probabilities are different. So the question is asking how do we solve the terms P and Q. Okay, so we say solve for P and Q. There we go. There's no need to actually find the terms or the numerical values of the terms, but you must express P or Q in a way that is directly solvable. So that means we need to boil everything down to one equation, or one equation that has one unknown. Okay, once we get to that point, then we can say it's okay, it's good. Okay, so let's take a look at this problem then. All right, so with the first one, okay, we know that in the first one, 0.576 is receiving everything correctly. So that means since we're transmitting a 1 to a 1 twice, so that means we have 1 minus p squared times 1 minus q just once, because we only transmitted a 0 once, but it's received correctly, so it's 1 minus q, because q is the probability of receiving something incorrectly. So that accounts for the 110. Now we look at the 101. Okay, with the 101, which has a probability of 0.16 associated with it, the first one is transmitted and received correctly, so we have 1 minus p. The second one is received incorrectly, so we have just p itself, and then the 0 is also received incorrectly, so we have a q here. And then the next one is 0.016 again, and that's the probability of receiving 110 as 011. So this time we have p going first, and then we have 1 minus p as the second term, and then we have a q as the third term. So it boils down to the same thing as the one above it, and that's why they're both 0.016, because they basically boil down to the same combination of 1 minus p, p, and q. And then the last one is 0.144, and that one is having a 1 received incorrectly, so that's a p. A 1 that is received correctly, that's 1 minus p, and a q that is received correctly, which is 1 minus q. Alright, so you look at all of these terms, and then you ask, well, how do we solve these things, right? So the trick to this question is we want to use the ratio between these four items in order to cancel out the unknowns on the right hand side. So obviously, if we divide the second and the third term, that's pointless, because we would have removed every single unknown term equals to 1. Okay, so that's not going to be very helpful. But if we look at okay, if we look at the first versus the last one, that can be quite helpful, right? So let's do that. So 0.576 divided by 0.144, the first versus the fourth one, is 1 minus p squared times 1 minus q, the whole thing divided by p times 1 minus p, times 1 minus q. Okay, the first thing is, hey, we just removed the term q, okay? But it's a little bit better than that too, okay? Because we can also cancel out one of these terms here. So we only got a 1 minus p on top and a regular p at the bottom. So if we move things around a little bit, okay, we can solve for that p. So we have to multiply p to the other side, okay, and then multiply this 0.144 to the other side over here. So that p is now gone, that 0.144 is gone. So that means we have 0.576p equals to 1 minus p times 0.144, right? I mean, you guys can probably tell how to solve the rest of this, but we can try to work this out. Okay, so we have 0.144 on one side, and then on the other side we have p times 0.576 plus 0.144. So now p can be solved by 0.144 divided by 0.576 plus 0.144. Okay, and I don't have to solve the actual numerical value because the question clearly states that as long as the equation looks pretty clear that we can solve for the unknown, that is sufficient already. So that's how I would kind of solve this particular problem. All right, so I think that's it for this particular live stream session. You're welcome. All right, cool. So if you guys have any additional questions, go ahead and ask, through Discord. I basically, will have, I have a lot of stuff that I still have to take care of. But from time to time, I will check on Discord, and if I see a particular question, and if it applies to the whole class, and I have time, then I'll go ahead and share another live stream. And I'll do it the same format, even if nobody may be around. I will still do it through live stream on Discord as well as recording on YouTube, just in case somebody wants to or has time to join me at that time. Then we can have a synchronous session to talk about these topics. All right, so I'm gonna drop out of live stream now. And remember, if you guys have any questions, just go ahead and type your question in Discord. You can put it in general, or you can put it on 2020-05-13. It will be pretty clear to me, as you guys already know, where you put the text message, so I can find it pretty easily either way. All right, cool. So I'm gonna drop out of the streaming now.